Sinem, would you take it away, please?
Hello everyone, my name is Sinem Govenkaya. I'm a research manager in the Interactive and Immersive AI group at IBM's TJ Watson Research Center. I'm also the Global Technical Lead for the IBM Technology Support Services Augmented Reality program. My team's mission is to create AI-driven innovations with particular focus on enterprise education and technology support. Let's take a quick look at how we use augmented reality in IBM Technology Support Services today. When we started our AR mission a few years ago, we had three important requirements. The first one was to create an AR application that works for repairing any target hardware without any prior training of object recognition algorithms. The second one was that it needed to enable collaboration in real time between remote support technicians and field technicians. And the third one was the requirement to run on everyday mobile devices without requiring any special equipment. To address this need, we've created IBM Augmented Remote Assist, which is a two-way collaboration application between field technicians and remote support experts. This has been in use with IBM Technology Support Services since 2017, and we have recently deployed it in Apple App Store for our clients to use as well. In July, we will be deploying an Android version of the application in Google Play Store. Augmented Remote Assist, as you can see, is enabling the field technicians to stream a live video of what they see in the field to the remote support experts, in this case the web user, who then annotates the scene with the right instructions, and those instructions appear in 3D on the field technician's view in the mobile device. So this is a two-way collaboration application. At a given time, the field technician can also annotate to ask clarification questions. The second capability we built for technology support services is Augmented Self-Assist. Augmented Self-Assist takes the remote support experts out of the equation by providing the instructions to the field technicians directly from the mobile app without having to contact an expert. Needless to say, Self-Assist has additional value on top of Remote Assist by cutting down the wait time, by enabling the users to do the repairs. And in this case, this is not just limited to the field technicians, but also for our clients to use. The challenge with generating an application like Self-Assist is really creating the content for it. Today, IBM Technology Support Services supports 65,000 products, and needless to say, it's not going to be possible to manually create content for such a big portfolio. Ideally, we should be able to dynamically generate the content on demand based on what's needed by the business. So how do we do that? Over the last few years, we've been exploring the concept of dynamic content generation, and our recent focus has been on the Doc to 3D concept. The idea is to leverage the how-to documents, which lay out the step-by-step instructions for the repair process and create 3D AR procedures as the output. Last year, we had proposed a 4-step framework for dynamic content generation. This year, we're extending that to 6 steps, and we're going to talk about how we use this framework to be able to generate content from documents. Let's take a look at how it works. The first step is understanding the repair instructions. So similar to last year, our approach is extracting the instructions from the documents, extracting the entities, which are the hardware parts, as well as the relationships of these entities with each other, to be able to understand what are the actionable entities that we should be highlighting in augmented reality. In the interest of time, I will not be covering the NLP pipeline, but suffices to say that we've added a bunch of different capabilities to address some of the shortcomings of our NLP pipeline last year, such as moving from heuristic-based approach to using Watson Discovery for smart document understanding to be able to scale the kind of exploration to any kind of document coming in. And I'd be happy to provide more details about the NLP pipeline at the end of the talk. The next step is recognizing the hardware parts. For this, we trained the Watson deep learning model to recognize the hardware parts, and we've used the same parts taxonomy that we extracted from document processing to ensure that the parts that we are labeling have the same names that were mentioned in the documents. In addition to this, we are making some adjustments and advancements to the object recognition algorithms by leveraging few-shot object detection in cases we have limitations to the number of images that can be stored during the AR sessions due to different restrictions in client environments and geographies. Next, we're going to take a look at how we relate instructions to the hardware parts. Now that we have a mechanism to recognize parts on the fly, the next step is labeling them using 3D AR labels. By taking the bounding boxes of the parts and casting a hit ray to the center, we are able to project the 3D labels dynamically. This helps us being able to create the labels on the fly without having to hard code them ahead of time. Another nice thing that this feature allows us is to create a finer level of granularity of understanding what hardware part needs to be highlighted in AR. So for example, if the instruction is talking about the screws on the fan, instead of highlighting all the screws, we would like to use the bounding boxes of the screws and the fan to be able to get to the right level of granularity and be able to label the correct screws. And if you have access to CAD models of the hardware, by aligning them with the 3D point cloud and making that investment one time, you're able to use the same parts over and over again every time you're creating a fan replacement procedure, CPU removal procedure, and so on. This creates a much richer experience compared to using labels and arrows in your AR procedures. The next step is detecting the hardware state. Let's start by defining what we mean by state. State really is a visual arrangement of hardware at a given point in time. As you can see from these pictures, for example, fan in versus fan out has a very distinct difference in the visual state of the hardware. Whereas something like CPU door up and CPU door down is a very subtle change. And it is going to be necessary to have advanced state detection algorithms to be able to do the recognition of such subtle changes. There are several challenges associated with creating a state detection algorithm. The first one is that you need to have complete visual perception, which is often not possible by a single camera shot. The second one is that the objects may only be recognizable from a certain viewing angle, and you also have the constraints of having to run this on mobile devices. Last year, we have published our work on an initial attempt to creating state detection at Mobicom, and there were a couple of interesting things that we've seen when we started looking into putting this into production. We had certain assumptions when we were creating the training data set that the remote assist users would be essentially labeling the regions of interest for us. Regions of interest are the areas of hardware that we are interested in tracking changes for. And the reality is that technicians are fairly busy during repair sessions, and they either do not have the time to do data labeling, or they will not remember to say that they have replaced the battery or removed the CPU. So this assumption did not hold. Instead, this year, we've moved on to creating regions of interests automatically. What we're doing is looking at the remote assist session usage and understanding which parts of the hardware the technicians are interacting with, and using those focus points to generate region of interest candidates that are later fed to the neural network model. In addition to this, we are also cropping the regions of interest so that we are removing the noise and we are only focusing on the areas that we are tracking changes for. This helps us increase our accuracy in detecting the state changes to a great length. Let's take a look at how state detection works. As the augmented reality user hovers over the hardware, the 4 regions of interests which have been identified for this hardware are getting cropped and tracked by the algorithm. You can see on the left corner the different 4 regions represented by the crop thumbnails. And the numbers that you're seeing at the top are showing the confidence levels of the state detection algorithm. As the user interacts with the system, the regions of interest information gets updated and fed to the neural network to identify the new state. Next, we're going to look at how we author augmented reality content in this framework. Oftentimes, when you dynamically create content, it becomes important to have an offline editor through which you can play back the content, edit it, and vet it. To address this need, we've created the AR Studio that you're seeing on the screen, which allows the users to use a dense point cloud of the hardware to be able to play back the annotations that were created from the procedures. They can also edit the annotations and add new steps to the procedures to be able to enhance the experience. To be able to create an authoring tool like this, an important requirement is to create a dense point cloud of the hardware so that we can have a way to visualize it. So we use 3D reconstruction mechanism to do this by leveraging the remote assist images that we capture from the sessions. When we started generating dense point clouds from augmented remote assist sessions, an important realization we had was the large number of cases where the resulting dense point cloud had holes. And needless to say, this makes them unusable and a poor experience for the user. This is due to the limitations in terms of the number and type of the images that we are sometimes able to store in remote assist sessions, which naturally leads to the holes in the dense point clouds. To address this need, we've come up with an ideal input frame identification algorithm, which essentially tells us what type of frames we should be storing from the remote assist sessions and which ones to avoid to lead to a denser point cloud. The second idea that we are working to remedy this issue is called semantic surface reconstruction. This enables us to take single RGB images of the hardware, as well as the 3D feature points associated with it from AR sessions, and produce a depth map which helps us to create a denser 3D point cloud. The idea is to semantically segment the objects in images, predict the surface normals for the images, and then reconstruct the mesh surfaces for those object instances. The result is creating a very nice and visually acceptable point cloud like this that the users can leverage during authoring sessions. The last step is the self-assist experience presentation. So now that we have all of the pieces of the framework, let's take a look at how the result looks.
Loosen the 4 screws on the fan and lift up the fan.
As you can see, state detection is in place. It identified that we're at step 3, and the instruction has been played to the user, who then takes the action. As soon as the state changes, it gets recognized and the new instruction is presented. Despite the fact that this is a subtle change, the system is able to understand it and give us the correct instruction. I would like to conclude by talking about what's next. In our team, we are focusing on creating different innovations for the technology support domain, one of which is the IBM Virtual Assistant for Technical Support. This gives the users a way to create chatbots at scale, and we are interested in merging our AR capabilities with the virtual assistant so that we can provide a more dialogue-like interaction for our users. In addition, we are interested in pursuing action detection for compliance. There's already quite a bit of work in the space by the IBM MIT Watson AI Lab, and we would like to leverage that work as part of our AR capabilities to ensure that we can guide the users to take the right action as part of our procedures. I would like to conclude by thanking this talented team of researchers, engineers, and creative artists for all their contributions to our project. Thank you.
Thank you very much, Sinem. Very interesting talk that you provided based on your real research and practical applications. Very, definite benefit to the real world. Um, it seems more like futuristic to me if you're a Star Trek fan, but what you were showing there with your mobile device. I just wanted to uh, share a question here. Uh, when will the type of AI-enabled AR solution presented become cost-effective for the SMB market? And do you see these types of solutions being delivered direct or through solution providers?
Are you able to hear me now?
Yes.
Okay. Yeah, thank you. I'll answer the second part of the question first. So the solution that we presented today is available in multiple different forms, and I think it will be beneficial in multiple different forms, meaning not only the service providers can provide it to provide, for example, support using remote support technicians or having the expertise themselves to help build the content through bootstrapping, remote assist kind of source. But also, as time goes on and the information and the kind of experiences that we can build accumulates, I believe it will also be possible to create subscription model type of experiences or have other providers to also sell similar content. So I don't think it's just limited to the service providers, but because the service providers have the expertise and the domain knowledge and the resources to create the content, I think that's the starting point. In terms of when it becomes profitable for and small and medium markets, I think it depends very much on the kind of hardware support and the variety of the products that they have in their portfolio, right? If it's only a couple of products, of course, it makes sense to use the time to manually polish and create the content needed. But the minute this it basically becomes more than a handful of products, it gets out of hand. So I believe that even for small and medium businesses, this solution would be profitable given a larger portfolio.
Thank you very much. You talked a lot about AR technology, 3D scanning, and everything. What other technologies do you see that are needed in terms of, leveraging what you mentioned, quantum earlier, obviously infrastructure questions, people with their cell phones, so 4G, 5G, and beyond. Uh, what do you think in terms of the kind of demands and the other types of technologies that would be needed to enable your technology?
In terms of the other technologies, so I think there are a couple of things that you mentioned. So 5G is going to be critical for every kind of streaming application to yield a seamless user experience, right? When we started doing the project, we were still in the 3G eras. And people, of course, cannot benefit from the technology, no matter how cool it is, how great it is, if they're not able to stream the video or see what the other person is seeing, for example, in the case of remote assist application that I talked about. So some of the advancements in the networking and also the communications are going to be key to enable these kinds of seamless experiences. The other things that I'm actually seeing that will change the game is about privacy. So where are we allowed to collect the data and leverage that data to be able to create these self-enablement experiences? If you have limitations in terms of privacy, how are you overcoming those? Are you using some of the AI capabilities to segment out things that are deemed sensitive and not supposed to store, or are you going to be clever about what you pick to store from the remote assist type of sessions, so that you still have sufficient amount of information necessary to create these self-assist experiences. So that's another area coupled with AI advancements that I think we need to overcome. And overall, right, computer vision is advancing, different AI capabilities, AI tracking is in pretty decent shape. And all those continue to evolve. Smartphones and the AR glasses continue to evolve. So I think we'll see richer and richer experiences in the near future.
Excellent response to that. And you introduce additional topics that are not necessarily deep technological, but you talked about the ethics, the security, privacy. But that's yet a whole new conversation that unfortunately we've run out of time. I want to thank you very much, Sanem. Excellent talk, a lot of great feedback from everybody, very favorable. They enjoyed your talk. And with that said, I'll conclude our session. Thank you very much. And just for everybody's awareness, we will have a 20-minute break. And please come back to the AI in XR track. Thank you very much.
Thank you.